Picture this, a place in the universe where gravity is so strong that not even light can escape, a place where time slows down and the laws of physics as we know them begin to break down. This isn't science fiction, it's a black hole, one of the most mysterious and awe-inspiring phenomena in the cosmos. But how do these cosmic giants come to exist? What happens when a star, after burning brightly for millions or even billions of years, meets its dramatic end? Today, we're diving into the incredible story of how black holes are formed, from the fiery birth of stars to the explosive supernova that leave behind these enigmatic voids. By the end of this video, you'll not only understand the science behind black holes, but also gain a deeper appreciation for the forces that shape our universe. So let's embark on this journey together and uncover the secrets of these cosmic wonders. Now turning to the very beginning of a star's life, let's explore how these cosmic powerhouses come into existence. Stars are born in vast, swirling clouds of gas and dust known as stellar nurseries. These clouds, often hundreds of light years across, are the cradles of star formation. Over time, gravity begins to pull these particles together, causing the cloud to collapse inward. As the material condenses, it heats up, eventually reaching temperatures so high that nuclear fusion ignites at its core. This is the moment a star is born. Nuclear fusion is the process that powers stars, including our own sun. It occurs when hydrogen atoms collide under immense pressure and heat, fusing together to form helium. This reaction releases an enormous amount of energy in the form of light and heat, which counteracts the force of gravity trying to crush the star inward. For millions or even billions of years, this delicate balance between gravity pulling in and fusion pushing out keeps the star stable and shining brightly. But this balance is only temporary. Eventually, the star will exhaust its fuel, setting the stage for the dramatic events that can lead to the formation of a black hole. This incredible journey begins with the birth of a star, a process as beautiful as it is fundamental to the story of black holes. Now turning to the next phase of a star's life, let's explore how it evolves from its stable main sequence phase into a red giant. Most stars, including our Sun, spend the majority of their lives in what's called the main sequence phase. During this time, they are in a delicate equilibrium, with the outward pressure from nuclear fusion balancing the inward pull of gravity. This balance allows the star to shine steadily for millions or even billions of years, depending on its size, but this stability doesn't last forever. As the star burns through its hydrogen fuel, the core begins to change. Once the hydrogen in the core is exhausted, the star can no longer sustain the same level of nuclear fusion. Without the outward pressure from fusion, gravity starts to take over, causing the core to contract and heat up even further. Meanwhile, the outer layers of the star expand outward, cooling as they move away from the core. This expansion transforms the star into a red giant, a phase marked by its enormous size and reddish glow. The red giant phase is a dramatic transformation. The star's outer layers can swell to hundreds of times their original size, engulfing nearby planets in some cases. Despite its massive size, the core of the red giant is incredibly dense and hot, now fusing helium into heavier elements like carbon and oxygen. This new fusion process generates energy, but it's only a temporary solution. Eventually, even this fuel will run out, setting the stage for the star's final act. The balance between gravity and radiation pressure becomes increasingly unstable, leading to the next critical phase in the star's life cycle. This evolution from main sequence to red giant is a crucial step in understanding how stars pave the way for the formation of black holes. Now turning to the next phase, let's explore how a star's life comes to an end, a process that depends heavily on its mass. For smaller stars like our Sun, the journey ends relatively quietly. After the red giant phase, these stars shed their outer layers, leaving behind a dense, glowing core known as a white dwarf. This remnant slowly cools over billions of years, fading into a dark, cold object. It's a peaceful conclusion, but not all stars meet such a gentle fate. For more massive stars, the story is far more dramatic. When these giants exhaust their nuclear fuel, they face a catastrophic collapse. Unlike smaller stars, their immense gravity overpowers any remaining outward pressure, causing the core to implode. This collapse triggers a violent explosion known as a supernova, one of the most energetic events in the universe. In a matter of seconds, a supernova can outshine an entire galaxy, releasing more energy than the star emitted over its entire lifetime. The explosion scatters the star's outer layers into space, creating a glowing nebula rich in heavy elements like iron, gold, and uranium. These elements, forged in the heart of the dying star, become the building blocks for new stars, planets, and even life itself. But the core of the star doesn't just disappear. Depending on its mass, it can collapse into a neutron star, an incredibly dense object, or if the mass is great enough, it can form a black hole. Supernovae are not just spectacular cosmic fireworks, they are the birthplaces of black holes. When the core of a massive star collapses beyond a certain point, no known force can stop it. The core's density becomes infinite, and its gravity so intense that not even light can escape. This is the moment a black hole is born, a point of no return in the fabric of space-time. The explosive death of a star marked by a supernova is the dramatic prelude to the formation of one of the universe's most mysterious objects. As we move forward, we'll dive deeper into the mechanics of these explosive events and how they set the stage for the creation of black holes. Now, turning to the heart of these cosmic explosions, let's take a closer look at supernova, the universe's most powerful fireworks. When a massive star reaches the end of its life, the core collapses under its own gravity, triggering a supernova. This explosion releases an unimaginable amount of energy, equivalent to the brightness of billions of stars combined. For a brief moment, the supernova can outshine its entire galaxy, lighting up the cosmos in a dazzling display. The shockwaves from a supernova ripple through space, compressing nearby gas and dust clouds. These shockwaves can trigger the formation of new stars, making supernova not just destructive but also creative forces in the universe. The explosion also scatters heavy elements like iron, gold, and uranium into space, enriching the surrounding regions with the building blocks for planets, moons, and even life. What's left behind after the explosion depends on the mass of the original star. For stars with a mass between about 8 and 20 times that of our Sun, the core collapses into a neutron star. Neutron stars are incredibly dense, packing the mass of a star into a sphere just a few miles across. A single teaspoon of neutron star material would weigh billions of tons on Earth. But for the most massive stars, the core collapse doesn't stop at a neutron star. If the core's mass is greater than about 3 times that of our Sun, no known force can prevent it from collapsing further. The core's density becomes infinite, and its gravity so intense that it warps space-time itself, creating a black hole. This is the ultimate fate of the most massive stars, a point where the laws of physics as we know them break down. Supernova remnants, like the Crab Nebula, serve as cosmic gravestones, marking the sites of these explosive events. These glowing clouds of gas and dust are not just beautiful to observe, they also provide valuable clues about the processes that lead to the formation of neutron stars and black holes. As we continue, we'll explore the next critical phase, the core collapse that sets the stage for the birth of a black hole. Now turning to the core collapse, the moment when gravity takes complete control, let's dive into what happens when a massive star's core can no longer resist its own weight. Throughout a star's life, there's a delicate balance between the outward pressure from nuclear fusion and the inward pull of gravity. But when the star exhausts its nuclear fuel, this balance is shattered. Gravity, relentless and unyielding, begins to dominate. As the core collapses, it heats up to unimaginable temperatures, reaching billions of degrees. The outer layers of the star, no longer supported by the core's pressure, crash inward at incredible speeds. This inward rush creates a shock wave that rebounds outward, triggering the supernova explosion we discussed earlier. But the core itself continues to collapse, compressing into an ever smaller and denser object. For stars with a core mass between about 1.4 and 3 times that of our Sun, the collapse halts when the core becomes a neutron star. But for the most massive stars, the collapse doesn't stop there. If the core's mass exceeds about 3 times the mass of our Sun, no known force can counteract gravity's pull. The core continues to shrink, becoming infinitely dense, and space-time around it bends to its will. This is the birth of a black hole. The conditions required for a black hole to form are extreme. The core must be massive enough to overcome the pressure of neutron degeneracy, the last line of defense against gravity. Once this threshold is crossed, the core collapses into a singularity, a point where density becomes infinite and the laws of physics as we know them cease to function. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. This process, though violent and chaotic, is a natural consequence of the life cycle of the most massive stars. It's a reminder of the incredible forces at work in the universe, shaping the cosmos in ways we are only beginning to understand. As we move forward, we'll explore the event horizon, the defining feature of a black hole, and what it means for anything that crosses it. Now turning to the event horizon, the defining feature of a black hole, let's explore this mysterious boundary that marks the point of no return. Imagine standing at the edge of a massive waterfall, where the water flows so fast that once you step over the edge, there's no way to climb back up. The event horizon works in a similar way. It's the invisible line around a black hole where the gravitational pull becomes so strong that nothing, not even light, can escape. Once something crosses this boundary, it's gone forever, swallowed by the black hole's immense gravity. The event horizon isn't a physical surface or a solid barrier. Instead, it's a region in space where the escape velocity, the speed needed to break free from gravity, exceeds the speed of light. Since nothing can travel faster than light, anything that crosses the event horizon is trapped. This makes the event horizon the ultimate one-way street in the universe. It's the point where the black hole's grip becomes inescapable, and it's what truly defines a black hole as a black hole. But why is the event horizon so significant? For one, it's the boundary that separates the known from the unknown. Beyond it, our understanding of physics breaks down. The laws of space and time as we know them no longer apply, and the mysteries of the singularity, the infinitely dense core of the black hole, lie hidden. The event horizon also plays a crucial role in how we detect black holes. Since black holes themselves don't emit light, we rely on the effects they have on their surroundings, like the way matter spirals into the event horizon, heating up and emitting radiation before it disappears. The concept of the event horizon also challenges our understanding of reality. It's a place where time slows down dramatically due to the intense gravitational field. If you were to watch an object fall toward the event horizon, it would appear to slow down and eventually freeze, never quite crossing from your perspective. Yet, for the object itself, it would pass through the boundary in an instant, pulled inexorably toward the singularity. As we continue, we'll delve deeper into the heart of a black hole, exploring the singularity and the mind-bending physics that govern it. But for now, the event horizon stands as a stark reminder of the immense power of black holes and the limits of our understanding. It's a boundary that both defines and conceals one of the universe's most enigmatic phenomena. Now turning to the singularity, the heart of a black hole, we find ourselves at the very core of one of the universe's greatest mysteries. At the center of every black hole lies this infinitely dense point where the laws of physics as we know them cease to function. Imagine squeezing all the mass of a star or even an entire galaxy into a single point so small that it has no volume. That's the singularity, a place where density becomes infinite and space-time curves to an extreme that defies comprehension. The singularity is where gravity becomes so intense that it warps the fabric of space-time itself. In this region, the curvature of space-time becomes infinite, meaning that the usual rules of geometry and physics no longer apply. Time and space as we understand them break down, and our current theories, like Einstein's general relativity, reach their limits. This is why the singularity remains one of the most puzzling and debated concepts in modern physics. It's a place where our understanding of the universe hits a wall, and where new theories like quantum gravity might be needed to explain what truly happens. One of the most mind-bending aspects of the singularity is its infinite density. When a massive star collapses, all its matter is compressed into an infinitely small point. This creates a gravitational pull so strong that not even light can escape, which is why black holes are, well, black. But what does infinite density really mean? In practical terms, it's a concept that challenges our ability to imagine or measure. It's a point where the very idea of size and volume loses meaning, and where the universe seems to fold in on itself. Despite decades of research, the singularity remains shrouded in mystery. Scientists are still grappling with questions like, what happens to matter when it reaches the singularity? Does it simply vanish, or is it transformed into something entirely new? And what lies beyond the singularity? These questions push the boundaries of our knowledge and remind us that black holes are not just cosmic curiosities, they are windows into the deepest secrets of the universe. As we continue to explore the mysteries of black holes, the singularity stands as a symbol of the unknown. It's a reminder that even in our age of advanced science, there are still phenomena that challenge our understanding and inspire us to keep searching for answers. With the next phase of our journey in sight, we'll turn our attention to the different types of black holes and how they shape the cosmos around them. Now turning to the different types of black holes, we find that these cosmic phenomena come in a variety of sizes and origins, each with its own unique story. Black holes are generally categorized into three main types: stellar, supermassive, and intermediate. Let's start with stellar black holes, which are the most common and form from the dramatic collapse of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses, triggering a supernova explosion, and what remains is a dense remnant, a stellar black hole. These black holes typically have masses ranging from about 5 to several dozen times that of our Sun, and they are scattered throughout galaxies, including our own Milky Way. Next, we have supermassive black holes, the giants of the universe. These colossal objects can have masses equivalent to millions or even billions of suns. Unlike stellar black holes, supermassive black holes are found at the centers of galaxies, including our own, where they play a crucial role in shaping their surroundings. The exact process of how supermassive black holes form is still a topic of intense research. Some theories suggest they grow from the merging of smaller black holes, while others propose they form from the rapid accumulation of gas and dust in the early universe. Regardless of their origins, supermassive black holes are thought to be central to the evolution of galaxies, influencing star formation and the movement of matter on a cosmic scale. Finally, there are intermediate black holes, which occupy a mysterious middle ground between stellar and supermassive black holes. These black holes have masses ranging from hundreds to hundreds of thousands of solar masses, and their existence has been harder to confirm. While stellar and supermassive black holes are relatively well documented, intermediate black holes remain elusive. Scientists have detected potential candidates in dense star clusters and through the observation of gravitational waves, but much about their formation and behavior is still unknown. Some theories suggest they could form from the merging of smaller black holes or from the collapse of massive gas clouds in the early universe. Ongoing research aims to uncover more about these enigmatic objects and their role in the cosmos. As we explore these different types of black holes, it becomes clear that they are not just isolated curiosities but integral parts of the universe's structure. From the remnants of dying stars to the colossal giants at the heart of galaxies, black holes come in many forms, each contributing to the intricate tapestry of the cosmos. With the next phase of our journey in sight, we'll delve deeper into the fascinating world of supermassive black holes and their profound influence on the universe around them. Now turning to supermassive black holes, these cosmic giants are truly the titans of the universe. Found at the very heart of galaxies, including our own Milky Way, supermassive black holes are millions to billions of times more massive than our Sun. Their immense gravitational pull shapes the galaxies they inhabit, influencing everything from the movement of stars to the formation of new ones. But how do these colossal objects come to be? The answer lies in a combination of cosmic processes that scientists are still working to fully understand. One leading theory suggests that supermassive black holes form through the merging of smaller black holes. Over time, as galaxies collide and merge, their central black holes can spiral toward each other, eventually combining to form a single, more massive black hole. This process of growth through mergers could explain how supermassive black holes reach such staggering sizes. Another theory proposes that these giants form from the rapid accumulation of gas and dust in the early universe. In this scenario, massive clouds of material collapse directly into a black hole, bypassing the star formation stage entirely. This rapid accretion of matter could allow supermassive black holes to grow to enormous sizes in a relatively short period of cosmic time. Take, for example, Sagittarius A, the supermassive black hole at the center of our Milky Way. With a mass equivalent to about 4 million suns, Sagittarius A is a prime example of how these objects dominate their galactic environments. Observations of stars orbiting close to Sagittarius A have provided crucial insights into its properties and behavior, helping scientists piece together the puzzle of how supermassive black holes form and evolve. Despite their immense power, supermassive black holes are not destructive forces in the way we might imagine. Instead, they play a vital role in regulating the growth and structure of galaxies, acting as cosmic engines that drive the evolution of the universe. As we continue to explore the mysteries of supermassive black holes, one thing is clear: these giants are not just fascinating objects of study but key players in the story of the cosmos. From their formation to their influence on galaxies, supermassive black holes remind us of the incredible scale and complexity of the universe. With the next phase of our journey in sight, we'll delve into another intriguing aspect of black holes, the enigmatic primordial black holes and their potential role in the early universe. Now turning to primordial black holes, we enter a realm of cosmic mystery that challenges our understanding of the early universe. Unlike stellar or supermassive black holes, which form from collapsing stars or galactic mergers, primordial black holes are thought to have originated in the chaotic moments following the Big Bang. These hypothetical objects could have formed from the extreme density fluctuations in the infant universe, where pockets of matter collapsed directly into black holes without the need for stars or galaxies. This makes them a fascinating subject of study, as they could hold clues about the conditions of the universe in its earliest stages. One of the most intriguing aspects of primordial black holes is their potential connection to dark matter. Scientists have long puzzled over the nature of dark matter, the invisible substance that makes up a significant portion of the universe's mass. Some theories suggest that primordial black holes could account for at least a portion of this mysterious matter. If these black holes are scattered throughout the cosmos, they could explain some of the gravitational effects attributed to dark matter without the need for entirely new particles. However, this idea remains speculative, as detecting primordial black holes poses significant challenges. The search for primordial black holes is complicated by their small size and elusive nature. If they exist, many could be as small as an atom or as massive as a planet, making them incredibly difficult to spot. Unlike supermassive black holes, which emit detectable radiation from their accretion disks, primordial black holes might not interact with their surroundings in ways that produce observable signals. This has led scientists to explore indirect methods, such as looking for the gravitational lensing effects they might produce or the ripples in space-time caused by their collisions. Despite the challenges, the study of primordial black holes offers a tantalizing glimpse into the universe's origins. If confirmed, their existence would not only reshape our understanding of black hole formation, but also provide new insights into the early universe and the nature of dark matter. As we continue to probe the cosmos with advanced telescopes and detectors, the search for these enigmatic objects remains a frontier of modern astrophysics. With the next phase of our journey in sight, we'll explore how black holes can form in binary systems, where the interplay between two stars creates some of the most dynamic and energetic phenomena in the universe. Now turning to black hole formation in binary systems, we explore one of the most dynamic and fascinating processes in the cosmos. Binary star systems, where two stars orbit a common center of mass, provide a unique environment for black holes to form and interact. In these systems, when one of the stars exhausts its nuclear fuel and collapses into a black hole, it doesn't just fade into obscurity, it begins to influence its companion star in dramatic ways. The gravitational pull of the newly formed black hole can strip material from its companion star, creating a swirling disk of gas and dust known as an accretion disk. This disk becomes a hotbed of activity as friction and magnetic forces heat the material to extreme temperatures, causing it to emit intense radiation, particularly in the form of X-rays. These X-rays are often the telltale sign of a black hole's presence in a binary system, allowing astronomers to detect and study these cosmic phenomena even when the black hole itself remains invisible. The dynamics of these systems are incredibly complex. As matter spirals into the black hole, it releases enormous amounts of energy, sometimes producing jets of particles that shoot out at nearly the speed of light. These jets can extend for thousands of light years, impacting the surrounding space and even influencing the evolution of galaxies. The interplay between the black hole and its companion star can also lead to periodic outbursts of energy as the rate of material transfer fluctuates over time. One of the most famous examples of a black hole in a binary system is Cygnus X1, discovered in the 1960s. This system consists of a black hole and a massive blue supergiant star, with the black hole pulling material from its companion and producing powerful X-ray emissions. Observations of systems like Cygnus X1 have provided invaluable insights into the behavior of black holes and the processes that drive their growth. As we continue to study these binary systems, we uncover more about the intricate dance between black holes and their stellar companions. This knowledge not only deepens our understanding of black hole formation, but also sheds light on the broader mechanisms that shape the universe. With the next phase of our exploration in sight, we'll delve into the structure and behavior of accretion disks, the swirling rings of matter that feed black holes and power some of the most energetic phenomena in the cosmos. Now turning to the structure and behavior of accretion disks, we dive into the swirling rings of gas and dust that play a crucial role in feeding black holes. These disks form as material from a companion star or surrounding space is pulled in by the black hole's immense gravity. Instead of falling directly into the black hole, the material spirals inward, creating a flat, rotating disk that can stretch for millions of miles. The accretion disk is far from a calm, orderly structure. As particles within the disk move closer to the black hole, they collide and generate friction, which heats the material to incredibly high temperatures. This heat causes the disk to glow brightly, emitting radiation across the electromagnetic spectrum, from visible light to X-rays. In some cases, the disk can reach temperatures of millions of degrees, making it one of the hottest regions in the universe. Magnetic fields also play a significant role in shaping the behavior of accretion disks. These fields can twist and channel the superheated gas, creating powerful outflows and jets that shoot away from the black hole at nearly the speed of light. These jets can extend far beyond the disk itself, sometimes spanning entire galaxies, and are a key feature of some of the most energetic phenomena in the cosmos. The inner regions of the accretion disk closest to the black hole are where the most intense activity occurs. Here, the material moves at incredible speeds, approaching the speed of light as it nears the event horizon. The energy released in this region can outshine entire galaxies, making accretion disks some of the brightest objects in the universe. One of the most striking aspects of accretion disks is their variability. The rate at which material flows into the black hole can fluctuate dramatically, leading to sudden bursts of energy and changes in brightness. These fluctuations provide astronomers with valuable clues about the black hole's environment and the processes driving its growth. As we continue to study these glowing rings of matter, we gain deeper insights into how black holes consume and transform the material around them. This knowledge not only helps us understand the life cycle of black holes, but also reveals the intricate connections between these cosmic giants and the galaxies they inhabit. With the next phase of our exploration in sight, we'll examine the powerful jets of particles that some black holes produce and how these jets shape the universe around them. Now turning to the powerful jets of particles that some black holes produce, we enter a realm of cosmic particle accelerators that defy imagination. These jets, shooting out from the poles of certain black holes at nearly the speed of light, are among the most energetic phenomena in the universe. But how do they form, and what impact do they have on the space around them? The story begins with the accretion disk, the swirling ring of superheated gas and dust we discussed earlier. As material spirals inward, some of it doesn't fall into the black hole. Instead, it gets funneled along the black hole's magnetic field lines, which act like cosmic highways, directing the material toward the poles. Here, the intense magnetic fields and rapid rotation of the black hole combine to launch jets of charged particles into space at incredible speeds. These jets can stretch for thousands, even millions of light years, far beyond the boundaries of their host galaxies. One of the most famous examples is the jet from the supermassive black hole at the center of the M87 galaxy. This jet, captured in stunning detail by the Event Horizon Telescope, extends over 5,000 light years and glows brightly as it interacts with the surrounding gas and dust. The impact of these jets on their surroundings is profound. As they travel through space, they collide with interstellar material, creating shock waves that heat the gas and trigger the formation of new stars. In some cases, the jets can also suppress star formation by blowing away the gas and dust needed to create new stellar systems. This dual role makes black hole jets key players in shaping the evolution of galaxies. But the jets aren't just cosmic sculptors, they're also natural particle accelerators. The particles within these jets are accelerated to nearly the speed of light, producing high-energy radiation like gamma rays. This radiation can be detected across vast distances, giving astronomers a way to study black holes and their environments in incredible detail. As we continue to observe and analyze these jets, we uncover more about the extreme physics at work near black holes. From their formation to their far-reaching effects, these cosmic particle accelerators remind us of the dynamic and interconnected nature of the universe. With the next phase of our exploration in sight, we'll delve into the ripples in space-time known as gravitational waves and how they reveal the secrets of black hole collisions. Now turning to the ripples in space-time known as gravitational waves, we enter a new frontier in our understanding of black holes. These waves are like the echoes of massive cosmic events created when colossal objects such as black holes collide or merge. Imagine dropping a pebble into a still pond. The ripples that spread out are similar to how gravitational waves propagate through the fabric of space-time, carrying with them the story of the events that caused them. The first direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, marked a monumental moment in science. This discovery confirmed a prediction made by Albert Einstein over 100 years ago and opened a new window into the universe. Since then, LIGO and other detectors like Virgo have observed numerous gravitational wave signals, many of which originate from the mergers of black holes. When two black holes spiral toward each other, their immense gravitational pull distorts space-time, sending out waves that travel at the speed of light. As they get closer, the waves grow stronger, culminating in a final, violent collision that releases an enormous burst of energy. This energy ripples outward, detectable even billions of light-years away. The signals captured by LIGO provide a wealth of information, from the masses of the black holes involved to the speed and direction of their spin. These observations have not only confirmed the existence of black holes, but also shed light on how they form and evolve. For instance, the detection of gravitational waves from black hole mergers has revealed that some black holes are far more massive than previously thought, challenging our understanding of stellar evolution. Additionally, these waves have provided evidence for intermediate mass black holes, a category that bridges the gap between stellar and supermassive black holes. The study of gravitational waves is still in its early stages, but it has already transformed our understanding of the cosmos. By listening to the whispers of space-time, scientists are uncovering the secrets of black holes and the violent events that shape the universe. As we continue to refine our detectors and expand our observations, the future promises even more groundbreaking discoveries. With the next phase of our exploration in sight, we'll delve into the cosmic collisions of black holes and the dramatic processes that unfold when these giants merge. Now turning to the dramatic cosmic collisions of black holes, we witness one of the most powerful events in the universe. When two black holes come close enough, their immense gravitational fields begin to interact, pulling them into a deadly dance. As they spiral toward each other, they distort space-time, sending out ripples known as gravitational waves. These waves grow stronger and faster as the black holes draw nearer, culminating in a final, explosive merger. During this collision, the two black holes combine to form a single, more massive black hole. The energy released in this process is staggering, equivalent to converting several times the mass of the Sun into pure energy in a matter of seconds. This energy radiates outward as gravitational waves, carrying with it the story of the merger. The resulting black hole is often more massive than either of its predecessors, with a new, unified event horizon that marks the boundary of its gravitational influence. The observations made by LIGO and other detectors have provided incredible insights into these mergers. For example, scientists have detected black holes merging that are tens of times more massive than our Sun, challenging previous theories about how such massive objects form. These collisions also reveal details about the spin and orientation of the black holes, offering clues about their origins and the environments in which they formed. Visual simulations of these mergers based on LIGO data show the intricate spiraling motion and the final burst of energy as the black holes collide. These simulations not only help scientists understand the physics of black hole mergers, but also bring these cosmic events to life for the rest of us. By studying these collisions, we gain a deeper appreciation for the dynamic and ever-changing nature of the universe. As we continue to observe and analyze these cosmic collisions, we uncover more about the life cycles of black holes and the role they play in shaping the cosmos. With each new detection, we move closer to understanding the full story of how black holes form, evolve, and interact. And as we look ahead, the next phase of our exploration promises even more revelations about these enigmatic giants of the universe. Now turning to the growth of black holes, we delve into how these cosmic giants expand over time by feeding on stars, gas, and other matter. Black holes are not static, they are constantly evolving, growing more massive as they consume the material around them. One of the most dramatic ways this happens is through tidal disruption events, or TDE, where a star ventures too close to a black hole and is torn apart by its immense gravitational pull. When a star gets too close, the black hole's tidal forces stretch and compress it, pulling it apart in a process called spaghettification. The star's material is then drawn into an accretion disk, a swirling ring of gas and debris that spirals into the black hole. As this material heats up due to friction and magnetic forces, it emits intense bursts of radiation, often visible across vast distances. These flares of energy can outshine entire galaxies for a brief period, providing astronomers with a clear signal of a black hole's feeding frenzy. Tidal disruption events are not just spectacular to observe, they also offer valuable insights into the behavior of black holes. By studying the light emitted during these events, scientists can measure the black hole's mass, spin, and the rate at which it consumes matter. For example, in 2011, astronomers observed a TDE in a galaxy 2.7 billion light-years away, capturing the entire process from the star's disruption to the resulting flare. Such observations help us understand how black holes grow and influence their surroundings. But stars are not the only source of sustenance for black holes. They also feed on vast clouds of gas and dust, often found in the centers of galaxies. As this material falls toward the black hole, it forms an accretion disk, releasing enormous amounts of energy in the form of X-rays and other radiation. This process not only fuels the black hole's growth, but also shapes the galaxy around it, regulating star formation and influencing the evolution of entire cosmic structures. As we continue to study these feeding mechanisms, we uncover more about the dynamic relationship between black holes and their environments. From the violent destruction of stars to the steady consumption of gas, black holes are active participants in the cosmic dance, shaping the universe in ways we are only beginning to understand. And with each new discovery, we gain a deeper appreciation for the role these enigmatic objects play in the grand tapestry of the cosmos. Now turning to the relationship between black holes and galaxies, we explore how these cosmic giants play a pivotal role in shaping the universe around them. Supermassive black holes, often found at the centers of galaxies, are not just passive observers, they actively influence the evolution of their galactic homes. One of the most fascinating aspects of this relationship is the feedback mechanism, where the energy and radiation emitted by black holes regulate star formation and galaxy growth. When a supermassive black hole feeds on surrounding gas and dust, it doesn't just grow in size, it also releases tremendous amounts of energy. This energy heats up the surrounding material, preventing it from cooling and collapsing to form new stars. In some cases, the black hole's activity can even push gas out of the galaxy entirely, effectively putting a halt to star formation. This process, known as negative feedback, ensures that galaxies don't grow too quickly or chaotically, maintaining a delicate balance between creation and destruction. On the other hand, black holes can also have a positive impact on their galaxies. The jets of particles and radiation they emit can compress nearby gas clouds, triggering the birth of new stars. This dual role, both suppressing and stimulating star formation, highlights the complex interplay between black holes and their environments. For example, in the galaxy Messier 87, the supermassive black hole's powerful jets have been observed carving out vast regions of space, while also igniting pockets of star formation along their path. The influence of supermassive black holes extends far beyond their immediate surroundings. Over billions of years, their activity shapes the structure and evolution of entire galaxies. Galaxies with active black holes often exhibit distinct features such as bright cores and spiral arms, while those with dormant black holes may appear more uniform. This connection between black holes and galaxy morphology underscores their importance in the cosmic ecosystem. As we continue to study these interactions, we gain a deeper understanding of how black holes and galaxies co-evolve. From regulating star formation to sculpting galactic landscapes, supermassive black holes are key players in the story of the universe. Their presence reminds us that even the most mysterious and seemingly destructive forces can have a profound and lasting impact on the cosmos. And as we uncover more about these relationships, we come closer to understanding the intricate dance that shapes the galaxies we see today. Now turning to the challenge of observing black holes, we step into the realm where theory meets reality. Black holes, by their very nature, are invisible. They don't emit light, making them nearly impossible to see directly. So how do scientists study these cosmic enigmas? The answer lies in observing their effects on the surrounding environment and using cutting-edge technology to peer into the darkness. One of the most groundbreaking achievements in this field came in April 2019, when the Event Horizon Telescope collaboration unveiled the first-ever image of a black hole. This historic image captured the supermassive black hole at the center of the galaxy Messier 87, located 55 million light-years away. The image revealed the black hole's shadow, a dark region surrounded by a glowing ring of hot gas swirling at nearly the speed of light. This glowing ring, known as the accretion disk, is what allowed scientists to visualize the black hole's event horizon, the point of no return. The Event Horizon Telescope, or EIT, is not a single telescope but a global network of radio telescopes working together as one. By synchronizing data from telescopes across the globe, the EIT achieves an unprecedented level of resolution, equivalent to being able to read a newspaper in New York from a cafe in Paris. This technique, known as very long baseline interferometry, allows scientists to piece together detailed images of objects that would otherwise remain hidden. The image of the M87 black hole was more than just a scientific milestone. It was a triumph of human ingenuity and collaboration. It confirmed key predictions of Einstein's theory of general relativity, such as the shape of the event horizon and the bending of light around the black hole. It also provided a tangible glimpse into the extreme conditions near these cosmic giants, where gravity warps spacetime and time itself slows down. But observing black holes is no easy task. The data collected by the EIT is massive, requiring supercomputers and months of processing to produce a single image. Additionally, black holes are often obscured by dust and gas, making it difficult to capture clear observations. Despite these challenges, the success of the EIT has opened new doors for black hole research, paving the way for future discoveries. As we continue to refine our techniques and expand our understanding, the ability to observe black holes directly brings us closer to unraveling their mysteries. From confirming theoretical predictions to inspiring awe and curiosity, the journey from theory to reality reminds us of the power of human curiosity and the endless possibilities of exploration. And with each new observation, we take another step toward understanding the universe's most enigmatic objects. Now turning to the fascinating effects of black holes on time, we delve into one of the most mind-bending aspects of these cosmic phenomena: time dilation. Near the event horizon of a black hole, the gravitational pull is so intense that it warps not just space but time itself. This means that time passes differently depending on how close you are to the black hole. For someone observing from a safe distance, time near the event horizon would appear to slow down dramatically. This phenomenon is a direct consequence of Einstein's theory of general relativity, which predicts that strong gravitational fields can stretch and distort time. To better understand this, let's use a thought experiment known as the twin paradox. Imagine two identical twins, one staying on Earth and the other traveling close to a black hole. The twin near the black hole experiences time much more slowly compared to the one on Earth. After what feels like a few hours for the spacefaring twin, they return to Earth only to find that decades or even centuries have passed for their sibling. This isn't science fiction, it's a real effect predicted by physics, and black holes provide the most extreme example of it. The implications of time dilation near black holes are profound, especially for the future of space travel. If humans ever venture close to a black hole, even a brief journey could result in returning to a vastly different future. This raises intriguing questions about the nature of time and our place in the universe. Could we use black holes as cosmic time machines? While the idea is tantalizing, the extreme conditions near a black hole make such a journey incredibly dangerous, if not impossible, with our current understanding of physics. Time dilation also has practical implications for studying black holes. For instance, light emitted from the accretion disk near the event horizon appears redshifted to observers far away, meaning its wavelength stretches out as it escapes the black hole's immense gravity. This redshift is a direct result of time slowing down in the strong gravitational field, providing scientists with valuable clues about the black hole's properties. As we continue to explore the mysteries of black holes, the concept of time dilation reminds us of how deeply interconnected space and time truly are. It challenges our understanding of reality and opens up new possibilities for how we might one day navigate the cosmos. With each discovery, we inch closer to unraveling the secrets of these enigmatic objects and the profound ways they shape the fabric of the universe. Now turning to the cultural impact of black holes, these mysterious cosmic objects have long captured the public's imagination, inspiring countless stories, movies, and works of art. From science fiction novels to blockbuster films, black holes have become symbols of the unknown, representing both the awe-inspiring power of the universe and the limits of human understanding. One of the most iconic portrayals of black holes in recent years comes from the film Interstellar, where a supermassive black hole named Gargantua takes center stage. The movie's depiction of the black hole's accretion disk and the warping of space-time around it was so scientifically accurate that it led to new insights in astrophysics. Yet it also took creative liberties to make the story compelling, blending science with imagination in a way that resonated with audiences worldwide. Black holes often serve as a canvas for exploring profound themes like time, mortality, and the human desire to explore the unknown. In Interstellar, the black hole becomes a gateway to new dimensions, challenging the characters and the audience to grapple with the complexities of time dilation and the fragility of human existence. This balance between scientific accuracy and creative storytelling is what makes black holes so fascinating in popular culture. They are not just scientific phenomena, but also powerful metaphors for the mysteries of life and the universe. Beyond movies, black holes have inspired artists, writers, and musicians to create works that reflect their enigmatic nature. From abstract paintings that capture the swirling chaos of an accretion disk to novels that imagine civilizations living near black holes, these cosmic objects continue to spark creativity. Even in music, black holes have been used as metaphors for emotional voids or transformative experiences, showing how deeply they resonate with the human experience. While popular culture often takes liberties with the science of black holes, it also plays a crucial role in sparking curiosity and interest in real-world astrophysics. Films like Interstellar and books that explore black holes have inspired a new generation of scientists and space enthusiasts, proving that art and science can work hand in hand to expand our understanding of the cosmos. As we continue to explore the mysteries of black holes, their portrayal in popular culture reminds us of the endless possibilities that lie at the intersection of imagination and discovery. Now turning to the conclusion of our journey through the mysteries of black holes, let's take a moment to reflect on what we've uncovered. From the dramatic collapse of massive stars to the awe-inspiring power of supermassive black holes at the centers of galaxies, we've explored how these cosmic giants come into existence. We've seen how stellar black holes form from the remnants of supernova explosions, while supermassive black holes grow to unimaginable sizes, shaping the very fabric of the universe around them. Along the way, we've delved into the mind-bending physics of singularities, the boundary of event horizons, and the ripples in space-time known as gravitational waves. Yet, despite all we've learned, black holes remain one of the greatest mysteries in the cosmos. Questions about their origins, their role in the universe, and the nature of the singularities at their cores continue to challenge even the brightest minds in science. The ongoing quest to understand black holes is not just about unraveling the secrets of the universe, it's about pushing the boundaries of human knowledge and imagination. As we close this chapter, remember that the story of black holes is far from over. Every discovery brings new questions, and every observation opens new doors to understanding. If you've enjoyed this journey through the cosmos, don't stop here. The universe is full of wonders waiting to be explored, and there's so much more to learn. Be sure to subscribe to this channel for more deep dives into the mysteries of space, science, and the incredible technologies shaping our future. Hit the notification bell so you never miss an update, and let's continue this adventure together. Until next time, keep looking up, the universe is calling.